Hello. We are learning the panel data model, and the learning example, the leading example, uh, was the relationship between the beer tax in a state and the traffic fatality in the state. So in general, we expect we expect higher beer tax will reduce alcohol consumption, and so it will reduce the number of traffic accidents, and so in the end, the traffic fatality will be lower. So we expect negative relationship. Higher beer tax implies lower traffic fatality. But as you saw in the previous lecture, the the regression from like 7 years regression data show some positive relationship, which is exactly the opposite of what we expected. And to understand that, we have to understand the panel data structure. The mystery, the puzzle was resolved once you include the panel data structure, and the idea was that there are several hidden factors such as the cultural attitude toward drinking, how generous toward drinking and driving, or what else, like say the traffic density, how crowded the area is, and there are a few other factors you can think of, and these factors are also very important factors of traffic fatality, but they are not observed. It's really impossible to observe the attitude, how generous uh, people in the state are toward drinking and driving. Then, however, we may we you don't need to worry about the unobserved variables as long as you can assume that those variables do not change over time. The cultural attitude, for example, it's quite persistent. As you can expect, culture does not change like that quickly. Like especially in our data, it's 7 years period. So within 7 years, it's hard to think that the culture has changed at all. So if you can assume that those omitted variables do not change over time, but specific to the state, then you may think that the starting points are different. Say Massachusetts, Texas, California have different starting point of the traffic fatality. So depending on their density, traffic density, and their culture, their traffic fatality would be different if all of them have zero beer tax, zero alcohol tax. And if alcohol tax increases, the higher alcohol tax may change the traffic fatality, but anyhow, the difference in the starting point dominates the effect of beer tax. That's why we find a strange positive relationship between the beer tax and traffic fatality. So the idea is instead of so after considering the omitted variable bias, which we assume to be persistent, time invariant, then the idea is we may like consider the different intercepts for different states that will fix the omitted variable bias. That's what we learned in the last lecture, and you may think it two different ways. It's not they are basically the same. The first the first approach is n-1 binary regressor form, which means if there are 50 states, for example, 50 states, then you can define 50 different dummy variables. A dummy variable takes, like this variable takes 1 if this is the state number 2, and otherwise 0. So, like this. And there are for each state, say there are dummy variable for New York State, dummy variable for California, dummy variable for Texas, for Massachusetts, like that. There are 50 dummy variables. And as we learned in the dummy variable trap chapter earlier, you have to drop one of them. Otherwise, including all 50 regressors, all 50 dummy variables will cause the perfect multicollinearity. So it won't work. So you have to drop one. So in the end, you have to include n-1 binary regressors, n-1 dummy variables in the regression model. Say beta 0 is intercept and x is vertex, and the others are dummy variables. This is maybe simpler way to imagine if you understand how the dummy variable is defined. But it's, as you can see, it's very cumbersome to have a long equation. So usually it's simplified to this. The traffic fatality y is a linear function of vertex plus the state-specific intercept. So I is a state, so we define the intercept of I, state I, as alpha I. So we call this state fixed effect. So state, in a certain state, there are the state-specific time invariant characteristics. So they determine the starting point, the initial point of traffic fatality. So that is, so state fixed effect, state heterogeneity. So anyhow, it does not change over time, but specific to the state. This is called fixed effects model. Fixed effects model is written in this way. That's what we learned in the previous lecture. And we will think about how the model work and what how we implement that, how the models work, or what's the potential problem in our case and in general. Think about this. So first, maybe a simple way to consider is simple way to implement that is define all the dummy variables. As I said, if you have 50 states, define dummy variables for them, and then include them in the estimation. Then you can just estimate all the things. Every parameter is estimated like by theta, so it should be easy. In our example, it's fine because there are only 50 states. Estimating 50 parameters is very simple in these days, by computer in these days. However, so 50 is just too small. Like usually, you have to think about much larger data set. So, for example, suppose that you observe 1,000 workers like over many years. Then there are 1,000 workers, and each of them have their own intercept. Like a state-specific effect, there must be worker-specific effect. And then you have to include 999 intercepts, dummy variables, which is impractical. Okay, 1,000 is okay, like to the computer. Computer can handle this, but extend it even more. Think about, so like say text data. So you have a perfect data set about all the taxpayers in the United States or in New York State over, like say in the past 20 years. I don't know how much taxpayers are in New York State, but it will be several, maybe million, maybe more, several 10 millions. That would be a problem even to the computer. So it's not practical, if not impossible. Also, even if it can be done, still, how can you read the outcome? The outcome will be like several million lines, so you cannot read the outcome at all, results at all. So it's not it's possible, but not practical in some cases. So then here I will introduce a simpler way to cancel out the fixed effects, the intercept. The idea is simple. The idea is, so we observe several time periods for each state. I will call the state, or you may replace state with individual or entity. So the textbook uses the term entity as a generic observational unit. Let me call this state. So for each state, we observe, in our example, 7 years. 7 years of 7 years traffic fatalities and beer tax. What you're going to do there is, so for each state, there are 7 observations. So you can calculate the average traffic fatality in that state. Say you observe 7 New York State's traffic fatalities. So there must be their average. And also, there are 7 New York State's beer tax rates. Then also you can calculate their average. And we will subtract the averages, their averages, state-specific average. So say YT is New York State's traffic fatality in 1982, and then subtract the New York State's traffic fatality average over the observation period. Also, beer tax in a certain year, subtract the average beer tax over the observation periods. So by doing this, we can show that it is easy to show that the time constant effect is canceled out, right? It's time constant. It does not change over time. So this effect remains in y and the average of y. So it must be canceled out. And you only handle x and u in the end. That is so. So average also satisfies this alpha. Average has alpha, so it will be canceled out if you subtract this from this. So now, like when you have 50 states, that's just canceling out 50 parameters. But so as I said before, if you have 1 million individuals in your data, then you are reducing the dimension of the parameters by 1 million. So just it cancels out a lot of parameters in your model. So it will help the estimation and your interpretation. So this is maybe the most common way to estimate the model. So in the end, you are interested only in beta 1. So you are interested only in the effect of beer tax. So beta 1 is maybe the only parameter of your interest. So if you don't care about the fixed effect, then this is canceling out the fixed effects will be more efficient. Say here, it explains exactly what I did. Say I equals to 1. The first state in the data is Alabama, and the first year is 1982, and then y tilde, the wiggle on top, is called tilde. Y tilde is defined as this. A typo. There should be tilde here. I had to fix it. So just transform all the observations into a deviation from the average, the deviation from the state's average. So it's entity-demeaned data. So we call this demeaned because we subtract the mean. So in the end, the mean will be 0. After subtracting the average, the mean will be this, must be 0. So that's why it's called demeaned variable. So then this is also very similar to the changes approach. Earlier in the last lecture, I showed you an idea to use 2 years. So if you use 1982 and 1987, then you can calculate their differences. So difference between 82 and 87. And then within the 7 years, within the like 6 or 75 years, some states may have the peer tax may have increased. Then using the increase in some states, you can see how much the fatality changed over time. So it uses the overtime changes in each state, and it is similar. Also, we are using changes, overtime change within a state, but by considering deviation from the mean. So if peer tax increases over time like this, increases, but mean is here, and then you calculate how much the peer tax was below the mean or above the mean. Then that variation is what we are using in this approach. So also the key idea is we would like to cancel out the fixed effects. And we can do that by considering this. Okay, we'll continue in the next video. See you later.